Good evening, everyone. I'm Will Thomas, the Spencer R. Ward Director of Research in History, Policy, and Culture here at the American Institute of Physics. Thanks, everyone, for coming tonight. I'm absolutely delighted to have you here for this, our fourth and final Line-Starling-Trimble event, public lecture event of this year. I'm very pleased to welcome Michel Janssen from the University of Minnesota. We'll have a fuller introduction in just a moment. I'd also like to take a moment to thank everyone who has donated to the history programs over the years. The Line-Starling-Trimble event is, of course, an endowed lecture series, and the American Institute of Physics accepts gifts through the AIP Foundation. We have a nice slide up here that talks about some of our programs. Team Up Together, which is a diversity program, our students' programs through the Society of Physics Students, and, of course, our DIBA initiatives, science policy, and the history and library programs, which I represent. So now, to introduce our speaker tonight, I'd like to hand the microphone over to our latest hire as a historian, Anna Dole. Anna, thank you.
Hello, everyone. I'm Anna Dole. I'm a historian at AIP, and it is my great pleasure to introduce today's speaker. Dr. Michel Janssen is a scholar of, excuse me, of intellectual history of physics, with a special interest in general relativity and quantum mechanics. Michel received his physics degree at the University of Amsterdam and his doctorate in the history and philosophy of science at the University of Pittsburgh. He publishes extensively. One of his most recent works, the second volume of Constructing Quantum Mechanics, came out in 2023 with Oxford University Press. For several years, Dr. Janssen lent his expertise to the Einstein Papers Project as an editor before joining the faculty at the University of Minnesota with a dual appointment in the program in the history of science and technology and the School of Physics and Astronomy. There, Michel puts the fear of physics in undergraduate students and instills historical thinking into physics majors. Today's talk is a look into the life and career of an early 20th century quantum physicist, Lucy Mensing. Welcome, Michel.
Okay. All right. Thank you all very much for coming. Thanks to the Center for History of Physics at the AIP for inviting me, and to Will Thomas in particular, and to Anna for introducing me. Anna and I actually overlapped and worked together on a survey course at the University of Minnesota. So I hope you had a chance to take a look at my abstract. So I'm going to be talking about Lucy Mensing, and first I'm going to turn off my phone, so that my wife doesn't call me like in the middle of the talk. Sorry about that. So in the quantum mechanics in the mid-20s is often referred to as like Knabenphysik, like boys' physics, because like many of the founding fathers of quantum mechanics were actually very young, were in their mid-20s themselves, right? So here's Wolfgang Pauli, born in 1900, Heisenberg in 1901, Dirac 1902, Jordan also 1902, and von Neumann in 1903, and so these were all male, right? Now, I'm going to be talking about somebody who's also very young, but female. And she was present at the creation of quantum mechanics, made some very, very valuable contributions herself, and as you can see, outlived them all. So this is Lucy Mensing. This is my favorite picture of her from 1928. And so the talk is based on an article that I wrote together with Gernot Münster in Münster. So yeah, Münster and Münster, on Lucy Mensing, and which is going to appear in a volume that is coming out of a project called WIQP, Women in the History of Quantum Physics. This is the new logo for the project, And it's going to appear in this edited volume, edited by Patrick Charbonneau, Michel Frank, Margriet van der Heijden, and Daniela Monaldi, Women in the History of Quantum Physics Beyond Knabenphysik. Okay? All right. So Lucy Mensing was born in 1901 in Hamburg, the oldest of 4 girls. And like her mother before her, she attended the St. Johannes Monastery School, known for its program to train teachers, the Lehrerinnen-Seminar. She graduated in 1920, decided to study physics at the then newly founded University of Hamburg. So this is a picture, a passport picture of like 21, like here's another one from 23, 24. So her most important teachers in Hamburg were Wilhelm Lenz, but he was in poor health, so most of the actual advising was done by who was then Lenz's assistant, namely Wolfgang Pauli. Right? So like even though Mensing and Pauli are roughly the same age, like she always looked upon Pauli as her teacher and her mentor. At Hamburg, she became friends with Ernst Ising. So you've heard of the Ising model of ferromagnetism. This is actually what Ising worked on for his dissertation with Lenz. It's also often known as the Lenz-Ising model. And so Ising was Jewish. So he was somehow able to hang on to his job to 39, then he was fired. And he and his wife Hannah then went to Luxembourg, where initially they were left alone. But in 1943, like he was forced into labor by the Nazis. In 47, they emigrated to the US. In the late 30s, like Mensing and Ising like sort of lost touch, but in the 50s they reconnected, and the Isings like actually like visited like Mensing in Germany. And so here is like a letter that Mensing wrote to the Ising couple about a visit to the Ludwig Museum in Cologne. If you haven't been there, I can highly recommend this. And so she writes, like, the painting Wild Boars of Mark reminded me of the Hamburg mandrill. It used to be taunted and mocked in my youth. Then the professor for literature in a class we, i.e. Ernst and I, attended once a week, discussed the mandrill, the colorful animal in the lush jungle, and we saw it with different eyes. I assume that one was also by Franz Marc. The painting is said to have disappeared during the war. Whether the Nazis had already taken it earlier and sold it to the SS, she doesn't know. All right. So here is the painting, like the Wild Boars, is a picture of Franz Marc. And here is like a portrait of Franz Marc by August Macke. I was like in Bonn last year, and in Bonn you have the Macke House, where you can see like many of these paintings. I've become a big fan of like this, the Blaue Reiter, like these paintings. And I'll show you a number of these. And so I was very struck by the fact that Lucy Mensing also liked these paintings. So this is the painting she saw, the Wild Boars. It's still up in at the Ludwig Museum. There it is. But the painting that she mentioned that she saw as a young student is like even more impressive. So this is it, the mandrill from 1913, which is currently in storage at the Pinakothek der Moderne in Munich. And so, like, I have this plan to write to the Pinakothek der Moderne to ask them to put it on the wall for the quantum year, and then putting a quote from this letter right next to it, right? So, oh, what happened here? Did I step on a cable or something? Maybe like if we sometimes it helps. It's back on. Okay. All right. Okay. So I think it would be great, like, you know, like as this should be the contribution of the Pinakothek der Moderne to the quantum year, that they put the painting out of storage on the wall and then have, like, you know, in German and in English, like the quote from the letter right next to it. All right. So she graduated, got her PhD March 30th, 1925, as you can see, like, in these notes, right? So a lot of what I'm going to tell you is based on like very fragmentary recollections that she jotted down in the late 80s. And so we got that material. So this is like Lucy Schutz. You'll see like later she marries like Wilhelm Schutz. So she's known as Lucy Schutz, like reminiscing in the 1980s. And my co-author, Gernot Münster, got all this material from the youngest daughter of Lucy Schutz, Dr. Dorothea Roloff. And she has told us that all these materials will eventually be deposited in the archive of the University of Jena, where they ended up. And so here's like, you know, from this document, right, after she got her PhD, I received a premium of 500 mark, and that was an award for her dissertation. Since I've become acquainted with life in Göttingen at the meeting, and we think this is some meeting of a local chapter of the German Physical Society, she says like there's a lot more contact between professors, assistants, and students, I used the prize money for an additional year of study in Göttingen. I arrived at Easter 1925, right around the time that the new quantum theory started with Heisenberg. Interesting time in physics. I used to have lunch with Heisenberg and Friedrich Hund, like another, you know, important player in the early years of quantum mechanics. So she produced, like in this year, like three papers. Two of them are really stellar, and the other one is like, you know, certainly a solid contribution. And so Mensing was actually the first to apply like the new quantum mechanics to diatomic molecules. She had already worked on diatomic molecules in the context of the old quantum theory right before she started work on her dissertation. And so these papers are like, so she wrote a paper, the rotation-vibration bands of diatomic molecules according to quantum mechanics in the Zeitschrift für Physik, submitted from Göttingen in March of 1926. That paper so impressed her advisor, Pauli, that Pauli invited her to work with him on a paper on the dielectric constant of dipole gases according to quantum mechanics. By this point, she is back in Hamburg, and so it's submitted from Hamburg. And a little later, she produces a third paper. So these are the stellar ones. This is like the solid one, interesting, but you know, like really, like these are the important ones. The intensity of the Zeeman components in the partial Paschen-Buck effect, and both the Zeeman effect and the Paschen-Buck effect have to do with the splitting of spectral lines in magnetic fields. So I want to look a little bit closer at the first two of these papers, and like. I'm not sure whether I should apologize for this, but I'm going to walk you through some of the actual physics in these papers. And I think if I didn't do that, I would really do like Lucy Mensing a disfavor, because like she loved like doing these calculations. This is not somebody who seems to have been overly concerned about like philosophical questions about like quantum mechanics. She really like enjoyed like solving these problems that were thrown up, and she was witnessing like, you know, this theory as it was developing in Göttingen. So I want to look at this first paper about the vibration-rotation spectrum of diatomic molecules, and this paper that she did with Pauli on the electric susceptibility of diatomic gases. Right. So even if you know, like math is not your thing, like, you know, hang in there. I try to keep this simple, but I do want to say something about this. All right. So let's start with the vibration-rotation spectrum. So this is a model of a diatomic molecule, right? So it can rotate and it can vibrate, and the spectrum that you see like is like in the infrared, and you have like a collection of lines with a missing line in the middle. Okay, so the old quantum theory could qualitatively, like, you know, explain this, and so so you have like these quantized energy levels. Characterized by two quantum numbers, one for vibration, N, one for rotation, L. These are the modern designations. So here, like, you have, like, you know, two of these, the vibration levels, and the energy is just the sum, like energy characterized by these two numbers, a vibration energy depending on N, and a rotation energy depending on L. So here's the N, and so, in fact, the vibration energies are much bigger than the rotation energy, so the gap is very wide, and then there's smaller deviations coming from rotation. So here's, I try to indicate this, right? But in fact, like, this distance is much bigger than the distance between these lines. Okay, that's the idea. And so now you have, the light is being sent out if you have transitions from these, between these states. And the allowed transitions are that you go from the vibration number N to N minus 1, but then L also has to go from L to L plus or minus 1. right? So this line, right, where you go from like n to n minus 1, but you keep L the same, this one is not allowed. But this one would, right? Now you go from L to L minus 1, and the other one that is allowed is this one, like you go from L to L plus 1. And so in the old quantum theory and in modern quantum mechanics, the frequency of the light that is being sent out is just the energy difference between these states divided by Planck's constant, right? So the length of these arrows then is a direct measure for like these frequencies. So you see that, so this is the central frequency, that is like forbidden. This is frequency is a little bit lower, that frequency is a little bit higher, right? If you combine it all together, you get that picture that we showed before. Very good. Now, so again, frequency of the missing line is just has to do with the change in vibrational energy, and the frequency shift around that has to do with the change in the rotation state, right? And then you get this. Okay, so now qualitatively, right? Quantitatively, right? You need to know, like, okay, what are these expressions for these energies? And so the rotational energy is like the angular momentum squared divided by 2 times the moment of inertia, right? For the physicists among you, like very similar to like, you know, momentum, like kinetic energy being equal to momentum squared over 2 times the mass, right? And so you see that to get this, like it really depends on like how you quantize like angular momentum. And this is the difference between the old and the new quantum theory. So in the old quantum theory, the angular momentum can only take on the values like an integral number times what we would now write as h bar, which is Planck's constant over 2 pi. So it's L h bar, where L can take on the values 1, 2, 3, and so forth, and so on. All right, so if you do that, you get something that is like almost right, but not quite. Okay. Now, what they did find is that if you use half quantum numbers, so you don't say like it's like an integral number times h bar, but a half integral number times h bar, that the agreement with the data is better. Okay? But unfortunately, it was completely unclear like where these half quantum numbers were coming from, and moreover, as we'll see in a bit, like these half quantum numbers in other areas made matters worse. So this was a bit of the puzzle. Okay? So now the new quantum mechanics, gives like new rules for quantizing the angular momentum. And these rules were introduced like in the famous Drei-Männer-Arbeit. This is a paper by Max Born, Werner Heisenberg, and Pascal Jordan, where it's sort of the first authoritative exposition of the new matrix mechanics. And remember, like Mensing was there as this paper was being written, so she would find out immediately that they had come up with these rules. And so now the rule says, like, you know, that the way to quantize this, you look at L squared, and it's not like little L squared times h bar squared. No, it's L times L plus 1. And the other thing that's important is that you can now have 0, and as far as Born, Heisenberg, and Jordan were concerned, you can have both integer and half integer values. Okay? So this was like, you know, the thing that Mensing started from. And one of the important results that she found and proved like in a more elegant way than other people at the time is like what is now a textbook result, namely that if you have orbital angular momentum as opposed to intrinsic angular momentum or spin, that the quantum number can only be the integer, not the half integer. Okay? So, all right, so now with this clarified, she's now going to apply these rules to like this, the vibration rotation spectrum. And now with this new rule, like everything comes out perfectly fine. And not only that, she can now also explain why it is that it looked as if these half quantum numbers like worked better. Because of this very simple like algebraic relation, right? L times L plus 1 is like the same as L plus a half squared minus a quarter. And so the minus a quarter doesn't matter, right? Because that means that you shift the energy levels on both sides by the same amount, right? Really, this part matters. So you can see that this new quantum rule gives effectively the same result here as having these half quantum numbers, right? So a very nice solution to this puzzle. All right, as I said, like this very much impressed Pauli. So Pauli invites her to write a paper on the something known as and I'll explain what this is about, the Langevin, the Baeyer formula for the electric susceptibility of diatomic gases. Again, diatomic gases, right? So this is the formula, right? So fortunately, it's a pretty simple formula. And so you notice that there is this factor like 1/3 here, okay? Now, in the classical theory gives that factor 1/3. I'll show you that in a bit. But Pauli had found that the old quantum theory changed that to 1.54, which is a factor 5 too large. And so his near namesake, the chemist Linus Pauling, had found that if you do half-integer quantum numbers, it gets even worse. Now you get a result that is almost 14 times too large. Okay, so they were quite puzzled by this. All right, so let me try to explain to you what's going on here, right? So you consider a gas of these diatomic molecules. And so these molecules, such as hydrochloride, so they have an electric dipole moment, right? So the hydrogen is a little positive, the chlorine is negative, right? And so now, you want to know about this electric susceptibility, typically indicated by the Greek letter chi, and that is a measure of how the gas responds to an external electric field. And that's a combination of two effects. So A, the electric field will pull the two poles a little further apart, and it will try to orient the dipole in the direction of the field, right? So this is why you have two terms in this equation, like this first term that's uninteresting for our purposes, that's the pulling apart. This term is what matters, that is this alignment effect. Right? And so, here's the definition of the, right? So the important part is you see the temperature there in the denominator. And so you can write it like this, and the correct formula has that constant is equal to 1/3. And now you see that the effect of this aligning is frustrated by the thermal motion of these dipoles, right? If these things are moving really rapidly, it's hard for the electric field to pull them in the direction of the field. So that's why the temperature appears in the denominator. So, so you would thus expect, right, that the greater the energy of the molecules, the smaller the contribution to this alignment effect. And that is precisely what you get in classical theory. Only the lowest energy state contribute, and the alignment effect is also the right size. You get exactly 1/3. And in the old quantum theory, it turns out that you get the alignment effect from higher energy states, which is puzzling, and you get contributions that lead to values that are way too high, 5/3 or 14/3. All right. So once again, the solution to the problem hinges on the way you quantize angular momentum. And so I'll walk you through this. So if you want to calculate this alignment effect, you need to take two different averages. So first, you need to take the time average of one of these molecules, in the direction of the field. And once you've done that, you need to take what is called an ensemble average, namely you need to average that over all the molecules in the gas. That's how you do it, okay? So in classical mechanics, you get that the time average is this expression over here. So you see the z component of the momentum squared times the length of the angular momentum squared. And if you average that over all of it, this is just going to be 1/3, because there's no preferred direction of x, y, and z. So it all works out very nicely. Great. Well, here's the old quantum theory, right? So the length of the angular momentum, the size, it's LH bar, and then the z component is quantized with this other quantum number, m, which can run from -L to +L, right? So there's 2L plus 1 possibilities for that. But note that the lowest energy state is now forbidden, so that cannot be responsible for this alignment effect. The time average over all allowed energy states still has that same factor, but now if you put in these quantization rules, that's equal to this, and the ensemble average over that does not vanish. Okay? Now, in a way, that's good news, because if it didn't, you would have no alignment effect at all. But it's also bad news because the alignment effect coming from these higher energy states is way too big. So this is the problem that Lucy Mensing was given by Pauli to solve, knowing now that she has to use these new rules for the quantization of angular momentum. So all right, so now, remember, L equals 0 is now allowed in the new quantum mechanics. And it turns out that that one state gives you exactly what you want, namely that you get the factor of 1/3. So now it becomes rather critical that everything else is going to vanish. And that looks like, like unlikely to happen, okay? So once again, you get that the time average is the same expression we had over here, but under this new quantum rule, this is the expression, right, that you get for the time average. Now they need to take like a ensemble average of that. Okay, how would you do that, right? So now it turns out that for every L that is not 0, this is going to vanish. So how would you do this? And so like I've thought about like how to explain this. If you all remember like calculating your grade, okay? So you get 9 grades, they're like weigh the same thing. So what do? You add all the grades together and you divide by the number of grades. That's it. So here, same thing, right? So you have like 2L plus 1 options. So you sum this all up and then you divide by like 1 over 2L plus 1, right? So you get this. It looks rather horrible, okay? Now, but if you look at it, you see this sum here. So this gives you like 2L plus 1 and the sum. So you get the sum here of these m squared. And it turns out that this is not immediately obvious, but it's a well-known formula known as the sum of squares formula. That this sum is exactly equal to 1/3 L times L plus 1 times 2L plus 1. And if you put that in, right, I hope you see this, right, that, so the L plus 1 disappears, 2L plus 1, there's minus that. This is indeed 0. I mean, I can only imagine how excited Lucy Mensing must have been when she, again, this is somebody who loved these calculations. This is just a key part of a very hairy calculation, when she saw that this all vanishes and she gets the result she wants. Okay? Pauli must also have been very pleased. Okay, so the gory details of this are in a paper I did with one of my grad students, Charles Midwinter. So, with obvious relief, so the paper has the italics here, only the molecules in the lowest state will therefore give a contribution to the temperature-dependent part of the electric susceptibility. Okay? Now, using an earlier paper of Mensing, that I talked about how to quantize the rules of quantization of angular momentum, my hero, John Van Vleck, at that point at the University of Minnesota, found the same result at around the same time, right? And was very disappointed that somebody had beaten him to the punch. Right? And so Van Vleck is, just to give you a sense of how important this result was, so in an interview with Kuhn in the early 60s for the Archive for the History of Quantum Physics, he said, in the old quantum theory, you got some wonderful nonsense, whereas it made sense with the new quantum mechanics. Right? And the first sentence of a classic book by Van Vleck on the father of modern magnetism, right, the guy who won the Nobel Prize, is the new quantum mechanics, is perhaps most noted for his triumphs in the field of spectroscopy, but its less heralded successes in the theory of electric and magnetic susceptibilities must be regarded as one of its great achievements, right? In fact, Van Vleck was so taken with this result that it still plays a very important part in his Nobel lecture, okay? And he actually produces, to show the wonderful nonsense, like this table about what happened to that constant, how it went way too big with whole quanta, half quanta, and then gets back to the classical value of 1/3. Now, I don't think that Mensing had any idea that this work of her cast such a long shadow. Right? At that point, she had long left physics. So what happened to her? Right? What did she do? She'd been in Hamburg working with Pauli. She'd been in Göttingen, right when it all started. What did she do next? She started actually considering teaching high school. Which was not a bad idea because like her chances of landing a professorship were zippo. And by teaching high school, she could at least keep her hand in with physics, right? And so as she writes in one of these reminiscences, she decided against this initially because I was shown a calculation suggesting that it would take 36 years to get a permanent school job. That later turned out to be false, but I was missing the third subject for a state exam. Instead, she went on this, she got a PhD, and she spent that year in Göttingen, as she says, at the outer frontier of progress, am vorderen Rand des Fortschritts. And then back in Hamburg, she says, now I'm going to get serious about that state exam. But then came the offer of a position in Tübingen, paid for by the Notgemeinschaft, with the emergency fund for for German scientists, started in 1920 to, for some financial relief of science. All right, so this is what she writes. She reminisces like in a letter to to a woman she knows. All right. So now, this didn't go well. So she continues writing. She says, there I miserably muddled through alone for a year and a half. I still had the topic suggested to me by Pauli. It was like a thankless topic. It's the Ramsauer effect. And so all you need to know about this, is that it's basically about like electrons passing through a noble gas, and that the probability of them colliding with other atoms in the gas is much lower than you'd expect classically. So, but it was not going as planned. The idea to take a train to Zurich to pay him a visit never occurred to me. I didn't have the money for it anyway. In 1928, I got married. As a woman, one could then no longer have a job. Okay? That's the end of it. So what I want to do is I want to sort of probe, like, how did this career that it started so nicely in Hamburg and Göttingen, how did it fall apart in Tübingen? And so I've been showing you this picture so far. This is like a picture of 1928, and I think in this picture, to me, like, she looks incredibly confident. Now here's an earlier picture. So I could have shown this, but here she looks not as confident, like, much demure, and so her, in a way, like, the confidence that she had as a physicist, like in Hamburg and Göttingen, kind of disappeared in Tübingen, and I'll tell you the story of that. So she became an assistant to this guy, Alfred Landé, and Landé probably hired her because of that third paper that I didn't go into about the Zeeman effect, because that, and the Paschen-Bach effect, because that was what Landé is an expert on, right? And so, like, for the physicists among you may be familiar with the Landé factor, which I think is the only result that Landé is still known for these days. And so, like, this was in Tübingen, this was like the mecca of spectroscopy under Friedrich Paschen. Ernst Bach was there. They had found the effect there in 1912. So Paschen was the director until 1925, and then he was succeeded by Walter Gerlach. And so Bach was also still in Tübingen during Mensing's time. And so here's a very charming, like, description by Mensing of the situation she found in Tübingen. The situation in Tübingen was as follows. Gerlach, right? So he is, of course, best known for the Stern-Gerlach experiment. Ruled the institute. He had about 25, 28 doctoral students. His only assistant was Schütz. Landé, the associate professor, had a room on the ground floor in which a second desk was placed for me. As a common room, there was a reading room next to the library, which was so small that sometimes 2 Japanese students studied their books in a squatting position, which I marveled at. All right. Now, Landé and Gerlach soon had a bad falling out, to the point that Landé just never showed up at the institute anymore. And Mensing says, like, never mind, that way he could never talk to his assistant, But their assistants, like Mensing and Schütz, they fell in love and became a couple. So Landé, he would emigrate. Landé was Jewish. He would emigrate to the U.S., not because of anti-Semitism, but because of this fight with Gerlach, who in the end was, like, kind of lucky, right? 2 years before Hitler came to power. And Gerlach would join, like, the German atomic bomb project in 1939. And so here's a picture of him, at Farm Hall, right, where they were, where these German nuclear physicists were detained at Her Majesty's pleasure, to make sure that if they turned them loose, that they were not going to defect to the Soviet Union. So here's a picture of Mensing and Schütz, like in Tübingen, and on the far right you see Landé. Let me see. So there's Landé. All right. And she had bad experiences in Tübingen. And the first one is like what I'll call the Bismuth affair. So during Mensing's time in Tübingen, the Dutch physicist Goudsmit, famous for the introduction of electron spin together with Uhlenbeck, and also is famous because of the Alsace mission, right? The mission that checked up on the German bomb project after the war. So in that capacity, he actually turned the tables on Gerlach, because like he was one of the people that was rounded up by this team. So he came to visit in Tübingen. And so Landé writes to him before his visit, he says, "It's particularly fortunate that in addition to you, Miss Dr. Mensing will spend a year in Tübingen, as she is really up to date on all new and old quantum methods. Her computational skills will certainly fit well with your ideas." All right. So now after Goudsmit had left, Landé wanted Mensing to keep working on a research project that Goudsmit had started with Bach. And so here is a letter from Mensing to Goudsmit. Lieber Sam, dear Sam, with regard to your and Bach's work on the fine structure of bismuth, Professor Landé has suggested that one can draw conclusions about the size of the magnetic moment of the nucleus. Following Landé's wishes, I've started to calculate this, but before I spend more time on it and before something short might be published about it, I wanted to ask you whether you have not long calculated the same thing yourself. That actually seems likely to me, since you already used most of the necessary formulas for the intensity calculations you plan to do. Okay? If you smell something like going on here, you'd be right, because like that same day, she sends a second letter to Goudsmit. And so in the second letter, she says, "For obvious reason, I am writing 2 letters to you today. The first, the physics one, I wrote in the presence of my boss, Landé, making sure he saw it. But I find it outrageous that Landé demands of me to meddle in your handiwork with bismuth, Sam. Had it been up to me, I would never have done that. I almost had a fight with him because I didn't want to do it." But enough about physics. And then you get a sense of like, how bad she feels. She said, "Except for physics, I'm doing very well here. But for a while, I just lived from one Sunday to the next and sat out the time in between in the institute. This is not a happy camper." In the meantime, there was also a very nice physics excursion. I think Schütz may have sent you some pictures of it. I was in high spirits and enjoyed it so much that I didn't know what to do with myself. Good thing it lasted only 3 days, as those hardly could have been topped. Right? So the contrast between the weekends and the weekdays is rather striking. And so right now, I would enjoy doing some physics again, but I can't think of anything sensible. I just confided in Pauli about my physics woes, and I'm waiting for his response. Now, we can actually identify that excursion that she got so excited about, and that can be inferred from a letter from Landé to Goudsmit in May of 27. So he says, two weeks ago, the whole Physics Institute had a 3-day excursion to the Black Forest, very beautiful, also pretty strenuous. The 100 kilometers or more would not have been up your alley, and Bach also did not join us in anticipation of the agonies. Miss Mensing, however, valiantly kept up with the 27 men. All right? And the destination can be figured out, this is like, as historians, like we like this, can be figured out from the pictures that we have. So here is like Mensing, like in the grass up front, and the sign that says Freudenstadt Igelsberg, right, which is a town in the Black Forest, like Gernot Münster, like figure that out. So here's Mensing. And here's another picture, a beaming Mensing with a huge backpack. Right, and so here, like you also see Landé, right? All right. So remember, he writes to her, "Miss Mensing valiantly kept up with the 27 men." What else did he say? So remember, he's writing to Goudsmit, who has now moved on to Copenhagen. He says, "I greatly envy you for the close collaboration with Bohr and Heisenberg in Copenhagen, especially in the new quantum theory. One's run into unsolved issues every day, which one would love to discuss with a physicist likewise interested in these questions. I'll probably be traveling to Zurich for that purpose at Whitsuntide to have a sensible conversation again with Mr. London." But like wait a second, right? So here, like in Goudsmit's PhD advisor, Paul Ehrenfest, he actually wrote to Goudsmit in November of 27. So please tell me in confidence about the future plans of London and Mensing, or of other young theories who catch your attention. Right? So Ehrenfest mentions like London and Goudsmit, London and Mensing just in the same breath. But Landé, on the other hand, is talking about like going, to Zurich to discuss physics with London while Mensing is sitting in his own office, right, that he never goes to, like in Tübingen, right? And so remember, like a year earlier, Landé had told Goudsmit, like, oh yeah, Mensing, she's really up on this stuff, right? But a year later, the only thing that he finds to mention about Mensing in the letter is that she kept up with the 27 men during the strenuous hike in the Black Forest, right? And so there's also a revealing letter that despite these troubles, Lucy Schütz stayed in touch with Landé. So Landé writes to the couple, he says, oh, the young couple from Tübingen, this is in '69, is already emeritus. Hard to believe when one looks at the old photos of the young physicist and the charming Lucy, the charmante Lucy. Okay? Like very, and this was not the only sexism probably that she had to deal with. Like her advisor, like is also on record as problematic. So according to Rudolf Pauls, Pauli thought that women only studied physics to find a husband. Okay, and so Pauls relates a story that at a conference, Pauli met a female theorist who had worked with him in the past, and it's got to be Mensing. Okay? Got to be Mensing. And says, like, found out she was married, and he said to her, like, so you succeeded off after all, right? Is es Ihnen also doch noch gelungen? Right? So it's so you can see this was not a good experience. Okay? Now, right on the heel, and in particular, like, you know, what it's also like clear from what we heard from her daughter, this idea that she had to meddle in the work of Goudsmit really, like, she found very distasteful. So this is why I'm calling this the Bismuth affair. So hard on the heels of that came the Ramsauer debacle. Right? Remember, that's what she's trying to do. I worked on the Ramsauer effect. That led to an essentially unknown mathematical function. I would start bright and fresh in the morning, calculating a piece of this function, right? I mean, this is what she likes to do. In the evening, the result would be x equals infinity divided by infinity. In the fall of 27, I wrote up this negative result and sent it to Zeitschrift für Physik. Pauli was in Switzerland. I could not visit him there, but I could have written to him. Of course, we know that she actually did, right? She just didn't remember, right? Remember, like, from contemporary correspondence, we know that she wrote to Pauli, like, you know, can you help me? My note appeared in the same issue in which a successful paper of a Swedish team appeared on the same topic with the help of a calculating machine. Now, that, as best as I can tell, that Swedish team also didn't really crack the Ramsauer effect, but nonetheless, Mensing was quite crestfallen over this failure. Right? And so these two things together, we believe, made her sour on physics. Right? We have, like, this is, you know, hard because we have, like, very fragmentary evidence. And this is also the impression that independently of us, the daughter came to. Right? So she wrote to Gernot Münster. She says, it's becoming increasingly clear to me that she did not leave science primarily out of a desire to start a family, but rather conversely, that she started a family because she could not cope with whatever kind of fighting was going on in the scientific world, right? So she did not have the taste for this rather cutthroat mentality that was, you know, rampant at this time. And right, remember what she says in 1977, I'm miserably muddled through, and now I got married, and you know, no job. And so it's probably no coincidence that she and Schütz got engaged. This is the picture. I'd like to note that they're sitting in a boat here, right? So that reminded me of another painting by Caspar David Friedrich, like, there was a big to-do in Germany. And so, like, you know, David Friedrich is famous for not being able to paint faces, always like people on the back, right? So here, but like the setting here is like very similar to what you have here, right? So, you know, like a little later, they got married. And continuing her recollection, she says, the next day I read in the paper that Wien had died, and I said, now Gerlach will become his successor. And that indeed happened. At the end of 29, Gerlach and the two of us followed him to Munich. And I went to Sommerfeld's lecture. In the morning, I attended Gerlach's classes, worked out the lecture notes. My husband dictated, and I wrote down parts of his handbook, which is something on magneto-optics. Or I dictated the barely legible text to an assistant. When I was writing myself, I was dreaming under the red setting sun about Freiburg, where she had been as a student, where my husband was on the list, right, of a list of possible professorships, and tried to conjure the call with the full force of wishful thinking. Now, this call to Freiburg never came. But so in 1930, they're still in Munich. She published her last paper and gave birth to the first of what eventually would be 4 children, a son Jürgen. So the couple would have 3 more, son Ulrich. Both the sons are dead. The 2 daughters, Cornelie and Dorothea, are still alive. And the 2 daughters were born after the family moved to Königsberg in East Prussia, now Kaliningrad in Russia, where Schütz was finally appointed professor for experimental physics in 1936. Okay. And so there's a beautiful recollection of them going to Königsberg. So she says she remembers a sleigh ride across the solidly frozen Pregel, like the river there, with the Mothus family. Did we have 2 sleighs? Did we take the children? I only remember a niece in a wonderful fox fur coat and a live fox that was crossing the Pregel. We saw it for a long time. As a city child, I'd never seen one except at the zoo. So I can't resist showing you another Frank Marc picture, namely the fox. And I actually saw this in Wuppertal, like when I was in Germany last year. What was the last paper about? This was once again on. I'm trying to. That was on something that she'd done in the old quantum theory, that she now revisits. I think it's about the breadth of spectral lines. It's a fairly short paper with a lot of references to the early paper. I don't know the exact details. It's nothing earth-shattering. Like it's sort of a competent piece of work. That's that is the that may be the one. Yeah. So that may be the one. Yeah. So I thought the 3 out there were the 3 I mentioned, but that is okay. That is the one. That's the one you saw. That's the line broadening. Yeah. All right. Thanks. So now I need to talk about sort of a painful part of the story, right? And that is that Wilhelm Schütz became a member of the Nazi Party. And so, all right, so he gets this appointment in Königsberg. But as you may have guessed, he actually replaced the Jewish professor for experimental physics, Walter Kaufmann, right? Well known among historians of relativity for doing measurements on the velocity dependence of electron mass, like in the context of the reception of special relativity. And so he was forced into early retirement at age 64. Likewise, another physicist, Fritz Sauter, replaced the Jewish professor for theoretical physics, Richard Ganz, who was dismissed at age 55. Okay. Now, Schütz joined the party in 37, the year after he was given the job. So he did not join the party to get the job. So it's kind of mysterious why he did this. But a letter from 1939 to a fellow physicist, Arthur Stewart, this is a notorious Nazi sympathizer and rabid anti-Semite, suggests that Schütz himself was also, at that point, an enthusiastic supporter of the Nazis. So that raises 2 questions, like how did Lucy Schütz feel about that? And the very fragmentary source material makes it very difficult to answer that question. The other question is how did she feel herself about the Nazi Party? That is easier to answer. Okay, so let me just go through this. So in that manuscript with memories, it's clear that Schütz had soured on the Nazis by 1943, but who hadn't? Okay. So she talks about the Kant Copernicus Fest, which makes it possible to date it exactly, because this was May 24th in 43, the 400th anniversary of the death of Copernicus, right? Copernicus and Kant being the 2 famous citizens of Königsberg. So she said, my husband was later always proud that he had nominated 2 non-party members as prize winners and prevailed, Heisenberg and Unselt. Well, that's interesting. Now, the rest of that passage is also interesting, though not for this particular question. So she says, we gave one of our very rare dinner parties. In addition to the guests of honor, we had the Motus and Sauter couples over. The former came 12 p.m. instead of 1 p.m. when we were still rearranging the furniture. I only had the Polish maid. And then the wild boar roast, which we had finally gotten that morning for 3 times the usual numbers of vouchers, after it had been promised for days, was hard as a rock. I was embarrassed when Heisenberg left a few vouchers. Unfortunately, I don't remember any of the conversations. Okay? So decades after the fact, she remembers the details of her hosting duties at that party, but she does not remember, like talking to Heisenberg to catch up. Maybe she didn't have even time to catch up with Heisenberg. Right? So as an aside, I find that interesting. Now, so after the war, a number of people wrote what are called persilschein. So persil is like is a laundry detergent. And so a persilschein is sort of a whitewashing document for your involvement with the Nazis, right? And to get reinstated at a German university, you had to present these notes. So, like one of them actually mentions Lucy Schütz as well, right? So it's the usual stuff. No, the guy really, was not a Nazi and never made a secret out of his rejection of National Socialism. And then he says, the same applies, perhaps in an even stronger and broader sense, to his wife. Right? All right. So how did she herself feel about this? Right? So now we saw, right, that the Persilschein says, well, she was even more anti-Nazi than the husband. She was friends with some Jewish physicists. I mentioned Ising, Goudsmit. She even stayed in touch with Landé. And she had, I showed you, she had like a very early appreciation for German expressionist art, which of course was considered degenerate by the Nazis. Okay? Now, I don't think this is going to convince any of you. You're going to say all right, anybody, they all had, any Nazi, she's hardly the only Nazi sympathizer with a few Persilscheins, a few Jewish friends, and you don't have to be a Nazi hater to be fond of German expressionism, right? And to underline that last point and give me an excuse to show you more paintings, I'll tell you the denouement of the story about the confiscation of these Franz Marc paintings, right? So his most famous painting, the Tower of Blue Horses, was actually put on display in this notorious exhibit of Entartete Kunst, the generous art, in Munich in 1937. But then, a group of World War I veterans protested because Franz Marc had actually died in combat as an officer of the German army, so the painting was removed. And Hermann Göring helped himself to this painting, and although he sold many to the US, he seems to have kept this one. All trace of this painting has disappeared, right? So just to show that, no, you can be a Nazi and love this kind of painting. Actually, in Minneapolis, a painting related to this is a very famous part of the collection. So this is the large blue horses, and so there's a lot of debate in Minneapolis about the provenance of this painting. Of course, where did this come from? All right. So where does this leave us? My feeling is that all indications are that Lucy Schütz was opposed to the Nazis, and there's no documentary evidence to suggest otherwise. What is puzzling is that this did not lead, as far as we can tell, to any sort of marital strife. The daughter, of course, difficult to ask her about this. She doesn't remember this. She was very young. So I will show you two other pieces of what I think is exonerating evidence. So this is her writing, and this is not for, she didn't write this for public consumption, right? This is a private letter. And she remembers that as a very young student, I was at a physics meeting in Leipzig. Their pamphlets against relativity theory were distributed, signed by about 10 or 20 names, most of whom were unknown to me. But one of the big ones says, how could Leonard sign something like this? So the evil already started that early. Could we and should we have prevented it at that point? And that is echoed in a letter that her friend Ernst Ising sent to her son Jürgen when Ising was working on a memoir. And so he says, I would like to insert a page about the faith of your family and about the thoughts that occupied your mother so strongly. What could or should we have done to prevent the honors? Right? So look, I don't have a close case, but I do believe that Lucy Schütz had no truck with the Nazis. All right, so there they are in Königsberg. It's bombed to smithereens, repeatedly bombed by the Red Army and the Royal Air Force. The last twice in the span of 4 days. First bombing didn't do that much damage. The second destroyed much of the inner city and the apartment of the Schützes, who then hightailed it to Jena, where Wilhelm Schütz had set up a branch of his institute. So there, after the war, in October 1946, they were in for an unpleasant surprise. So Russian soldiers knocked on their door and told them to pack up and get ready for a long journey. And so we actually have like a little note from her son, right? A postcard to relatives in Frankfurt, Frankfurt am Main, where Schütz was from. And she said, "Dear Aunt Annie, 5 a.m. this morning, we got the order to pack up our belongings right away. Then we were taken to the train station in a Russian military truck. Our furniture is in a freight car. We are sitting in a passenger compartment. Everything is guarded by soldiers. Besides us, other physicists and engineers have been put on transfer. Our destination is unknown. Warm greetings till we meet again." What happened? So the Schützes were taken to, how much time do I have?
We're supposed to be wrapping up in a few minutes.
Okay, so I don't have that much left. To the island of Gorodomya. I asked like my Russian colleagues how to pronounce it. I'm looking over at Anna. Gorodomya in the city of Ostashkov in the Operation Osofyakim, which was like the analog of the Operation Overcast in the US, where they rounded up a bunch of like German engineers and scientists to help with the reconstruction of the Soviet Union. Okay? And so there's lots of material on this among the papers, and they had to stay there like for 6 years. And so, so finally, she gets like like some letter, like after some delay, and writes back, says the second letter is so life-affirming and full of wonderful activity that one feels quite bitter here in exile. It's like peeking into a room all lit up for Christmas, yet not being allowed to enter. But then I tell myself that this Christmas room is nothing but a chimera, and that in reality everything is difficult and dreary over there as well. Here, at least, it's not our own ones who are doing this to us. Okay. So they get back to Jena. Guy gets this chair in experimental physics. I'm going fast now. And so, like they keep talking about physics. All the kids go into physics-related jobs. The husband dies. She survives her husband quite a bit. And then, in the 80s, she starts writing down these recollections. And what is striking about these recollections, and I'll stop reading the quotes, is that they are much more detailed about this failed year in Tübingen than about this very successful year in Göttingen. Right? And so there was a few reminiscences about Göttingen in a letter she writes shortly after the death of Heisenberg. And so she reads in the book, and so she says, well, I want to read you this. Like, I rejoiced about the 2 semesters we spent together in Göttingen, experiencing the new quantum mechanics from up close and making a small contribution to it. And then she continues to add, like, oh, and that, and the skiing, the bobsledding, and listening to the chamber music and all this, Schubert's trio in B flat, right? So it seems that she actually remembers, once again, like with this dinner party, the details of the social much more than the physics. Like, and what she says about the physics is like very generic and referent. Like, thankful that she was part of this, and like that I could make a small contribution. And so that's why, the title, like the Forgotten Quantum Pioneer, and I think she might have appreciated her own contributions better had she been interviewed for the Archive for the History of Quantum Physics. Now, she's living behind the Iron Curtain, but it could certainly have been arranged, right? And so her name came up in these interviews. So it comes up with Jordan, right, with whom she had worked, and Jordan actually says she was the first one to apply quantum mechanics. Like, I think that's wrong. I think Pauli certainly got it published first, but she still would be the second person to apply quantum mechanics to a real system. The exchange with Goudsmit is even more interesting. So he tells Kuhn, oh yeah, I was working with Mensing, right? And Kuhn says, are you in touch with her? Are you in touch with Fräulein Mensing? Now Mrs. Something or other. Well, it's Mrs. Schütz, but she's in the Soviet zone now. Could you write? Ja, says Goudsmit, right, being Dutch, but nothing came of this. Right? So Lucy Schütz never found out, like, how important her contributions were. So she moved in 92 to be close to her oldest daughter. The local newspaper ran a story about her, and the headline is, everything is interesting, one just has to start. This is this here, right? That she told her kids. And shortly thereafter, she died, and I'll leave you with some pictures of Lucy Mensing from her long life. Thank you.
Michel, thanks very much. We are at 7:30, so if anybody has to take off, by all means, feel free. No judgments here. I'll move a little bit closer. I would like to have time for at least a couple of questions, so I'll open it up right to the floor. Scott.
Thank you. Thank you very much, Michel. Excellent talk. I enjoyed every minute of it. Thank you for preparing this. I was unaware of Mensing, as I'm sure a lot of our colleagues are.
Yeah.
And so thank you for doing the research on this. You found some amazing material. Let me say two things. First of all, of course, it's very fascinating to find a female contributor to the early days of quantum mechanics. But I think there'll be a resonance of this story with young women in science today. I know many young women who've experienced not exactly the same circumstances, but who have had early successes and then have dropped out of science, physics, chemistry for kind of reasons which are about their integration into the physics community. Mm-hmm. So I think there'll be a resonance with that. But my serious question here is about Tübingen. Yeah. Now, you mentioned that there was a near simultaneous publication by some Swedish physicists, which then came up with a similar result, but was perhaps somewhat more refined because of what? Because of calculation devices. Mm-hmm. So I'm thinking probably Tübingen didn't have these.
That's probably correct.
Yeah, and so part of Lucy Mensing's disappointment with physics was that in her immediate surroundings, in the community that she was at in Tübingen, they didn't have the resources to really give her the tools she needed in order to do really top-level work and compete with those Swedes. You know?
That's an interesting suggestion, but like, we're going on extremely thin source material, right? I mean, I just showed you a few pages of these recollections, and then, it's amazing that we were able to put together like a story this complete just on the basis of that. So my impression with that is that Mensing enjoyed these pen and paper calculations a lot, and that if you look at her paper on the Ramsauer effect, I mean, I understand very little about the Ramsauer effect. But she says the model that they're using is just no good. And so I don't think at the end of the day, the calculator made much of a difference. I mean, if you run like a calculator on a wrong model, you still get like uninteresting results.
Well, you think she got infinity over infinity?
Yeah,
that's not for lack of a calculator.
That's right. Yeah. No, that's thank you. Yeah. So now on your first point, I just want to make a general comment, right? So this is part of this project, like WIQP, Women in the History of Quantum Physics. And there's of course a big literature about like women in science, like one of like Sally Kolstad at the University of Minnesota, is a big name in all this. So there is like a literature on this, but I don't know that literature very well, and so and neither does my co-author Gernot Münster. So we were very hesitant to make these higher level suggestions, like you were saying. So this is this is very much like a bottom up kind of story. So I just tell the story. And then I find it very interesting that you say, oh, I recognize that, right? But we consciously try to stay away from this and just tell her story, right? Thinking like, okay, this may resonate, other people may pick up on this and may put it in sort of into these broader schemes. Like in fact, when the paper was refereed, we were told you should do that. And we resisted, said, no, we just don't know that stuff. The best we can do is just tell this story and try not to get on a high horse all the time. Right, and that will be the most potent statement about what was going on here. Okay, so but I'm at the same time I'm pleased that you recognize oh yeah, this is a phenomenon that happens all the time. Yeah.
I have a slightly technical question about the Ramsauer effect that she worked on.
Yeah.
Was she using wave mechanics at that point?
She was using wave mechanics for that. Yes. Yes.
I guess I'll look at her paper.
Okay. No, if you in a way this is a guess, right? So I liked your response, if you get infinity over infinity, your problem is not that you don't have a calculator. But I would like to know, I'd like to know better, whether it's indeed the case that, you know, you just don't get this Ramsauer effect with the model that she's using. That's what she's suggesting in her own abstract, but of course that's before she's seen the Swedish thing. And then, like, she took it really hard. That is clear from the reminiscence. She took it really hard that this didn't work out. No, but like, I'd be happy to, you know, like, run it through Google Translate, clean it up for you, and send you a serviceable English translation. If you didn't tell me, like, you know, like whether you think this is a reasonable model or not. Okay.
All right, is there anything else? Yes.
I was wondering if you knew or had come across other of those whitewashing letters for other people being hired into the university communities, and if they also featured the spouses, attestations of the spouses as well, or if that is kind of an acknowledgement that Lucy Mensing is going to be influential in the physics work of her husband, and so she also needs to be mentioned in those letters. Is that unique to her?
All right, so I've seen a number of these, like Perseelschein documents. I'm not aware of anyone where the spouse is mentioned. And so, like, I just showed you this, like, very fast. But if you read, her daughter assures us that there is a whole, I mean, you can imagine that her daughter is trying to sort of defend her father, right? Who has a bad reputation. I'm not the first one to point out that he's a member of the Nazis. That Dieter Hoffmann did a real number on this guy. So the daughter is trying to defend, and she told us there's many of these Perseelscheine in the. She gave us this one because, like, that was unique in terms that Lucy Mensing is also mentioned in this. Now, I don't think reading this that this is because, like, she needed to be exonerated. She was not going to get a job, and everybody understood that she was not going to get a job. But she was a woman, right, married to this professor. So it is telling, I think, that this neighbor, who was really only asked to exonerate the husband, you know, mentions, like, oh, and actually, like, the person who was not much more anti-Nazi was his wife, you know. And so again, like, my suspicion is that it's thanks to Lucy that the neighbor was, you know, like, was willing to write for the husband, who clearly, like, you know, in 1939 was still, like, a very, very enthusiastic Nazi.
Thank you.
All right, well, thank you very much, Michel, for an absolutely wonderful talk. This was our last Line Starling Trimble event of 2024. We hope that you'll join us again in 2025. We are working right now on putting together a very nice program of lectures for you. So once again, Michel Janssen, everybody, thanks very much.
Thank you. Thank you.